Hello, my structural analysis friends. Up to this point, we've been doing shear and moment diagrams for beams. Today, we're going to turn our attention to frames or more complex structures. There's some minor steps that we've got to take into consideration as we look to apply loads to vertical members, horizontal members, and even inclined members. So we'll show you a quick example of how to do that, as well as some other little pieces of information that help when doing the analysis of more complex systems. So without further ado, let's get started. So the first example that we're going to look at today is a simple frame that consists of a horizontal beam being supported by a diagonal member. Okay, so instead of just being a horizontal beam like we've done before, we now have the effect of this, and this is where the challenge is going to lie. So if we look at it, we have point A is a roller, point C is the connection to the beam, and then point D is a pin support. From between A and C, there is a 10 kip vertical load acting at the midpoint downward and an 8 kip horizontal load acting at the midpoint to the right. And then there's also a distributed load across the top from C to D in the amount of 2 kips per foot. Now the dimensions are from A to C horizontally is 4 feet, and from A to C vertically is also 4 feet. So this guy is at 45 degrees. And then the beam is 5 feet from one end to the other as we start to look at this. Now, just like any good statics problem, the first thing you do is you figure out the support conditions and draw a free body diagram. And so that's what I've done in this picture. This is a roller, so clearly there's a vertical load here. And then this is a pin, so clearly there's a vertical and a horizontal is the way that I've chosen to choose these for my coordinate system. All right, so now we can do some simple statics and we can find out those values. Right, forces in the x, if I sum to the right positive, then the equation is 8 kips. That's this guy plus this dx. Dx is a negative 8 kips. So that tells me that this guy is really acting in the opposite direction. That negative sign is the one that we're watching. And that should make sense, right? Because I only have one horizontal effect, this load pushing the structure to the right. This is the only thing that can hold it back. Clearly, that's drawn backwards. Now, the reason that I did that is that I stuck to my right-hand rule sign convention, which is this. The right positive, up positive, and then counterclockwise positive is the way that we learned it back in statics. So that's the sign convention that I chose. And so when an answer down here comes out negative, it tells me that this is backwards. So that's how I knew that's to the right, to the left. All right, do the same thing for forces in the y. It's very simple. It's AY up, 10K down, 2 times 5 kips, 2 kips per foot times 5 feet down, and then a dy up is everything that we have happening here. And so I can write an equation that has a function of AY and dy. So I can't solve this any further, so I didn't simplify this yet. We'll come back around to this here in a second. Right. So to find the reaction AY, I'm going to sum moments at D, and that's because this is a pin support and there are 2 unknowns. I'll sum here, and then AY, all I have to do is just figure out, well, how far are all these forces from that point D? So the moment's force times distance. So if I'm looking at my AY force, the distance is 2 plus 2 plus 5 is 9. So that's this guy. It's going clockwise, so that's why it's a negative. And then I have a 10 kip point load here that's located at a distance of 5 plus 2 or 7 feet, and it's going counterclockwise, so that's a positive. And then the 8 kips is a distance of 2 feet down, okay, and it too is going counterclockwise, so that it's a positive. And then this guy is 2 kips per foot times 5 feet, and then times the distance to the centroid of the load, which would be half of 5 feet or 2.5. So that's what all this says. And if I do the math, I find out that AY is 12.33 kips acting upward, that location. And it was a positive value, so what I drew was correct. Okay, dy, on the other hand, then I can plug in back into this equation once I have the AY value, and I find out that dy is 7.67 kips acting upwards. Okay, so once we have that, now's the methodology that we need to look at. This is just basic statics. You guys know how to do this. Okay, what we have to do is we have to come back now and look at the individual pieces of the structure. Okay, and so what we're going to do is all members, shear moment diagrams are always drawn to a coordinate system that is aligned with the axis of the member. Remember when we did this beam, you know, we drew a shear diagram horizontally and we drew the moment diagram horizontally, just like what you would do here. Well, this guy's inclined, so all we're going to do is we're going to turn our paper and we're going to look at what's going on with this one. And it looks something kind of like that. But we've got to find a couple of things first. So we're going to cut this diagonal member off of the structure. And when I do that, you end up with a free body diagram that looks something kind of like this. Okay, and so again, I've left it at its inclined orientation and put all the stuff that I know. I basically cut this thing off just before the joint at C. And so if I turn my paper that way, it now starts to look a lot like everything that we've done before. This is my positive sign convention for a cut on the right side, if you remember back in the video. If you don't remember that, go back and look at that in one of the earlier videos. And so VC is acting down. MC is counterclockwise positive, which is what we expect. And NC is a tensile load is considered positive on our sign convention on this. So those are our unknowns. So to be able to draw shear moment for this member, I've got to find those internal forces at the joint, or just before the joint, if you will. Okay, now, part of the problem that we have is if I incline my paper, now I have forces that don't line up with the coordinate system. All the other problems we've done to this point, you know, my reaction is always aligned with the axis of the member, which is this line coming along here, and then these perpendicular lines that we use to help kind of segment and set up the graph. And so we've got to get all of these guys turned to align with this system. You have to do this step because VC and NC are always aligned with the longitudinal axis of the member and the perpendicular line that comes across the section. And so that's why these are oriented the way they are. That's the trick. That's the difference in this. Okay, so we've got to come in and figure out, get these guys converted over so I can now work with shear and moment. Okay, all right, and so we'll turn our paper back around and we'll kind of look at this. So all I'm doing is I'm looking, let's start with reaction at AY. So if I do AY to get myself onto that aligned, what I'm calling X prime and Y prime, to get my axes lined up. So my X prime is this direction and my Y prime is on that one. That kind of gets us our orientation. And so I can break this into components. That this force is the resultant of two forces on those two axes. So by components, it's going to be 12.33 kips times the cosine of 45. Gets me a number of 8.71. And then AY is also 12.33 times cosine of 45, or sine of 45, which is also the same number because it's a 45-degree angle. You got to be kind of careful here if we have an issue, if it's a non-45-degree angle. Okay, the other piece that we have to look at then is getting their directions correct. So the load is acting up, so then the components clearly have to be in that orientation to get me a resultant that comes up there. Okay, and so that's how I know their direction. So when we redraw our picture, we'll put those guys on in place of this one. Okay, do something very similar with the 8 kip load at B. All right, so here's my axis of my member, 8 kips horizontal. So to get my X prime, that's going to be 8 kips times the cosine of 45, 5.66. And then to get the vertical or that Y prime direction, it's going to be 8 kips sine 45 or 5.66 also. And so again, the force is acting to the right, so these are the components. And so this one's acting down on the beam, this one's acting up. Okay, and so you can see that those are the directions that we'll associate. And again, we'll replace those onto the picture when we get down there. Okay, and then last but not least, we do the exact same thing over here on the 10 kip load. 10 kips is acting down, here's the inclined line. All right, and so when I break this down to get this, then the P2Y prime is 10 kips times the cosine of 45 degrees is 7.07. Okay, and then P2X prime is 10 kips times the sine of 45 degrees or 7.07. Notice the sines and the cosines switch because now I'm talking about a vertical load. I'm trying to get that to a horizontal axis. Okay, and so if this load is acting down, then his components have to be oriented that direction. Right, so all I do now then is I go back and I redraw this picture with the corrected loads on it, and that's the diagram that you see happening right here. Okay, so here's my 8.71 up, 8.71 across. I have the 2 point loads. One gives 7.07 and the other gives 5.6. All right, sorry about that. So we have our components of our 8 kip and 10 kip load at 7.07 here and the 5.67 here for a total of 12.74. And then I have, this is the one that's a little tricky, that the 8 kip load put a 5.67 acting up and to the right. That was this one. Okay, at the same time, the 10 kip load is putting a 7.07 acting down to the left. So these two guys are fighting each other, right? And so, and then all my other unknowns are here. So what we're gonna do is we're gonna do the algebra and we're gonna simplify this down into one final set, which is on the next page, right? And then, so if I turn this thing, that was the orientation we were looking at. Okay, that member, if I lay it flat on here, ends up being 12.74 kips acting down, 1.4 kips to the left, 8.71 to the right at A, 8.71 up at A, and then my internals are here. Okay, and so now we go back and we do the statics to find these four guys real quick, just like you did before. So sum of forces X, 8.71 to the right, 1.4 to the left, and my NC has to be 8.71 minus 1.4 plus NC equals 0. NC is clearly a negative 7.31 kips. Okay, and it's pushing to the right. And so that basically means that since that force, we assumed a tension here, but it ended up being negative, means that this guy is actually putting a compressive force into that segment of the beam. All right, so we're going to actually have to draw another diagram that we don't normally draw that isn't a shear moment diagram, that is instead is an axial load diagram. And I'll show you how to do that here in a second. Okay, and then to get the rest of the unknowns over here, I'm going to do sum of forces in the Y, 8.71 up, 12.74 down, V down. Okay, so positive, negative, negative with the numbers substituted in. And if I do that, then my VC in this case ends up being a negative 4.03, which tells me that my shear is actually acting in the opposite direction. Okay, it's actually acting up. Okay, so, and we'll take advantage of that here in a second. Summing for the internal moment then is just like we've done before. I'm going to take 8.71 times. Now, the length is different because it was 4 over, remember originally it was that arrangement, and it was 4 and 4, so then this length ends up being 5.64, okay, and then these dimensions here are 2.82 feet. And so we'll need those because that's how we're going to sum the moments with their perpendicular distances. So 8.71 goes times 5.64, clockwise, negative. 12.74 counterclockwise, positive, and its distance is 2.82. So that's this number. And then everything else is times 0. NC, VC, and this guy are all acting through the point, so they don't get included in the equation. But I do have the applied moment, which is counterclockwise positive, so it's a plus MC. And if I do the math and the algebra on that, I get an MC equals 13.19 kip feet. Okay, and that was a positive value, so it tells me that was the direction that we're looking at. Okay, so now the challenge becomes, how do we draw the pictures? Okay, so if this is A, this is B, and this is C, we're going to start to kind of look at how we set ourselves up for this. Okay, so for the axial load, it's just kind of like drawing a shear and moment diagram, but we're going to look at the axial load on this one, okay, that we start with the first axial load of this 8.71 kips, and it's pushing on this member, so that's a compressive value. Because remember on the left end, it would be acting the other way to be tension. So this is a compressive value. So I'm going to call up tension, I'm going to call down compression on this guy. And so that value, if I draw it, goes in at, from here to here, it's constant all the way down the length. There's nothing that changes the axial load until I get to point B. Right, so it's minus 8.71 there, and I can call that as a negative, and then I can put that piece on there. Okay, now once I get to this point, okay, now this guy is acting on that point, and he's going to reduce that amount. Okay, and so I'm going to reduce it by an amount of 1.4 kips here. So this guy now moves up here, and then it's constant all the way across at a value of minus 7.31. So that's the axial load diagram for that particular member. So if you're designing this column, you're designing it for those two guys. So more than likely you're designing for him. Okay. All right, and so that will get us there. And so then I get over to here, and then I end up with that negative value. So I should be at a negative 7.31, which is what I have happening here. So it jives, and so that guy will then push me back to 0 as I come off the member. Okay, so that's the axial load diagram. Again, you've done this in mechanics materials, but it's a little strange to see it in the context of the structural analysis class, but I thought I would throw that in as well. Okay, so now let's do the shear diagram. Now it's just like all the other problems that we've ever done before. So my shear, the first point is going to go up 8.71 by the value of the reaction, and then we're going to be constant across and then down 12.74. So let's get those pieces laid in here. So first piece goes up positive 8.71 for my shape there. Okay, and then it's going to come down that 12.74 off of that value, which will put me here at a minus 4.03. Comes in here and it does this. So that's my positive. Shade this in. Negative, shade that in. Okay, and then when I come off the beam, I'm sitting at minus 4.03. Okay, and so if you look, that number should match the value of the shear that you got at that location, which it does. So we're good. All right, and then the last piece is we're going to do the moment. Okay, so it was a pin support, so it starts out at 0, and now all I need to do is I need to look at what the moment diagram is doing relative to this guy. Okay, and so we look at the amount that it goes up. It's going to be 8.71 times that distance, which is 2.82 feet. Because again, our distance here, it's up on the upper picture, but I'll draw it here so we remember 2.82 feet here. Okay, and so this is a constant load. That means that this guy has to be first order, so he's linear increasing up to here. Okay, and that number then, if I multiply 8.71 times 2.82 feet, that number should be, I have a math problem here. Let me fix this real quick. 8.71 times 2.82, that number should be 24.5. That's kip feet. Okay, it gets me to there. That's a positive because it's increasing. Okay, and then once I get to this point, now it comes down. Again, this is 2.82 feet here. All right, sorry about that. Inadvertently cut off the recording. All right, so if we look at this, so we're at 24.5 kip feet at the end of this, and that was because of this being multiplied by 2.82, so that's 24.5. And then when I come over and I subtract off the next dimension, which is now going to be 4.03 times 2.82 minus 4.03. Minus 4.0. Okay, this gets me down to what would be an amount of 13.19 kip feet, which is what it should be. Okay, and the amount that it dropped was equal to that area. Right, and it's constant here, so it needs to be linear here. Okay, and then that moment match the moment that we computed up here. So notice that the values that are on this diagram don't show up anywhere in it, but that final result is the exact same number. Okay, and that was the thing that I second guessed myself there for a second, but we're good on that. So, all right, and that's what we have. And so that's the moment diagram for this particular piece of the diagonal member. Now, in reality, we drew it horizontally, but in reality, it's actually oriented like this up the member. And then if we come back and do the beam, which is just like all the others that you've done, it would lay in horizontally, like along the edge. Okay, and so that would be the moment diagram. And we can go from the moment diagram to now guessing which way it deflects. Remember, a positive moment causes kind of a downward deflection. So this guy is kind of deflecting kind of down that direction. And so from that, you can actually start to get kind of a sense of the deflected shape of this thing. And it deforms as you might expect. So if I put this member back up here, what's happening is that this guy is bending down something kind of like that. Okay, and then this joint will maintain integrity, and then clearly this guy will do something very similar. Okay, but that joint that's here maintains the angle that it had before and after, and that becomes an important idea when we get into some of the more advanced analysis methods, is the joint continuity that exists between one member and another, and that's another difference on the frames that we'll talk about a little bit later as we move forward in the process. So anyway, hope that wasn't too confusing. We'll stop there.